Okay, guys, so we have a brand new topic starting this week, and we're going to run with this idea pretty much through the end of the semester. And the concept here is frequency response. Okay, so the frequency response concept tends to be challenging for students because we're stepping away from the time domain and we're jumping into something called the frequency domain. Okay, so you've had a little bit of exposure outside of the time domain when we looked at transfer functions in the S domain. Okay, so the S domain, you kind of had to wrap your head around this idea that the S domain is a complex domain as opposed to the time domain, which is sort of this one-dimensional domain. The frequency response is a completely different domain, and it just means that the independent argument or the independent variable is not time, but rather the frequency. Okay, I'll explain what that means in more detail as we go along, but I want to sketch out the main idea of the frequency response just right off the bat here. Okay, so we've been studying systems that have some input and some output. Okay, so P of S, this is just some dynamic system. It's some transfer function that represents some real life system. So it's kind of the same thing we've been doing all semester. Um, Now, what we have been doing in the past is we've been looking at different types of inputs. Okay, so the inputs that we've been looking at could be, impulsive, or they could be constant, like a step input, or they could be exponential inputs. They could basically any input that you want to apply, you could simulate that and look at the corresponding output y. Um, for frequency response, we are only concerned with one input, and it's not the input. I'm sorry, it's not the impulse. It's not the step. It's the sine wave. Okay. So for frequency response, we're always looking at an input that has a sinusoidal form, like sine of omega t. Okay, now the fundamental idea, the key concept behind frequency response is that if your system is linear and time invariant, which all transfer functions are, if we have a linear time invariant system and you apply a sinusoidal input like sine of omega t, the output is guaranteed to have a sine wave with the same frequency, right? So you input sine of 10t, the output's also going to be sine of 10t. However, the key idea here is that the output is going to be scaled. Okay, so it's going to be scaled vertically on the y-axis, and it may or may not be phase shifted by some angle phi. That's the main idea behind frequency response. Okay, so you hit a system with the sine wave, you're going to get an output uh, that's a sine wave at the same frequency. Okay. The key here is that this what's called scaling factor is called the magnitude. Right? It's called the magnitude, and this phase shift, well, that's just called the phase. And these two terms, it turns out that they are themselves functions of the input frequency that you apply at the sine wave. Okay, so more specifically, we could write the magnitude as really it's a as a function of omega, and that's going to change, right? As you apply different inputs, the magnitude and the output is going to change, and the same goes for the phase. So these are both functions of this very same input frequency here at U of t. Often, the magnitude and phase are written in terms of the plant itself. So often, instead of A of omega, we'll write it as the magnitude of P of j omega. Right? These are just different ways of writing the same thing. So magnitude can be written as A of omega, or often it's written as magnitude with the vertical bars of P of j omega, which is the frequency response function. And I'll explain that in just a little bit as well. For the phase, we often write this phase angle phi by the symbol for angle, and we can express it as the angle of P of j omega. Okay, P of j omega, that's a frequency response function, which we'll talk about a little bit later, but the main idea again is for any LTI system, okay, you hit it with the sine wave, you are guaranteed to have a sine wave of the same frequency in the output. It's just that the output may be scaled vertically and it may be phase shifted horizontally. Okay, that's the primary idea behind the frequency response. To illustrate this idea, what I thought I could do is to basically set up a little demonstration. And this is very, low tech. This is very low tech, but I think I still like this demo because it brings a physical element to this very conceptual idea of the frequency response. Okay, so what we have here is the following. Okay, so there's like a flat surface, like a desk or a table. Okay, and on top of that table, there's just a piece of paper, something that can move back and forth. Okay, so I can apply a sinusoidal input to this piece of paper. So I can basically slide the paper back and forth like so. And on top of that piece of paper, there's a mass. There's an object. Okay, and that object is sort of sitting on the piece of paper, so there's friction between the mass and the piece of paper. So, you can imagine if you apply a very low frequency sinusoid, there's not enough sort of inertia to break that coefficient of friction, so the mass will essentially just stick to the piece of paper. Okay. However, if you start to oscillate the paper underneath that mass more quickly, you might expect that it starts to slide. Okay, so the mass will slide with respect to the piece of paper, and we're going to consider the output of this particular system to be the horizontal displacement of the mass. Okay, so the input is the displacement of the paper, the output is the displacement of the mass, and we could run this demonstration to illustrate this idea of frequency response. Okay, so we're going to take a couple of cases here. For a very, very small frequency or very low frequency of oscillation, if the input is sine of omega small t, we know that based on the definition of the frequency response, the output displacement is going to be some scaling factor times the sine of omega small, right? That same frequency of the input, t, plus some phase shift. Okay, so plus some phase shift. Phi, we'll call that phi 1. Okay, so we can actually get this part by running this demonstration sort of live here. Okay, so what I'll do is I'll play we'll switch the view here so that you can actually see this setup on my desk here. Okay, so we'll start this, and what you can see is that for very low frequencies, essentially the mass, or the penny in this case, is just stuck to the piece of paper, right? The paper is oscillating, but the coin is not sliding or moving with respect to the paper itself, okay? Which means that if the input has a magnitude of, say, 1, and the mass is attached to the paper, then the output also has an amplitude of 1. So experimentally, we can determine the magnitude for a low frequency to just be a value of 1. Okay. At the same time, because the mass was physically attached to the piece of paper due to forces of friction, they were oscillating in phase with each other, right? Because they were stuck to one another. So there is no phase shift. So we actually have 0 degrees of phase for this particular system. Now what we can do is we can actually plot, okay? We can actually plot these two data points on a set of axes that looks like this. And notice that the independent variable in both of these plots is the frequency, okay? This is why it's called the frequency response, because it's all a function of the input frequency. Okay, so for the first plot, this is going to be that magnitude as a function of omega, which we often refer to as the magnitude of p. These are sort of one and the same. And for the second plot, we're going to look at the phase angle, which is often referred to as the phase of P. Okay, so we've got 0, minus 45, minus 90. We'll just set up these axes here. So let's say 1, 0.1, 0.01, maybe 10 will be up here. Okay. Okay, and so for a very low frequency like we had over here, okay, so a low frequency here, on the frequency domain, that corresponds to a value very far to the left. Okay, so for a very low frequency, we're somewhere here. And we'll call this omega small. Okay, now experimentally, we went ahead and determined the magnitude and phase at that very low frequency. So we can actually plot a data point. One's right here at a magnitude of 1, and one's right here at a phase of 0. Okay? So what we can do is we can basically do the same experiment. We can do the same experiment at a higher frequency. So at omega high, if we increase the frequency of oscillation of the base of this piece of paper, we're still going to get an output of the same form. Okay? We're still going to get an output that's some magnitude times the sine of omega high, so there's a high frequency, plus some other phase. Okay? Now these two values, this magnitude and phase for a high frequency, they're going to be different because the magnitude and phase themselves are functions of the frequency, but we can try to determine those experimentally as well. Okay, so let's see what happens as we sort of speed up. Okay, we're going to speed up the input frequency. We're going to speed up faster and faster and faster until at some point we get going pretty fast. And we'll jump into slow motion right here. That's pretty fancy, right? When we're in this slow motion phase, you can almost see that the mass is almost stationary, right? It's not moving very much at all. It's moving a little bit, but not that much. Okay, so actually what happens is for this particular system at a very high frequency, we're finding that magnitude is starting to approach 0. It's almost just stationary, sitting there while the paper sort of slides under that mass, right? I don't know if you caught it from the slow-mo. The slow-mo video kind of indicates that, right, due to the nature of this system, you have basically a piece of paper and an object on top. At a high frequency, I'm sort of pushing the paper, and so there's this frictional force on the mass, which is sort of pushing it forward. But before this gets a chance to really accelerate in this direction, I'm already sliding the paper back. So this is sort of out of phase motion as I'm going at a very high frequency. And it turns out for this nature of a system, which is essentially a mass damper system, that for very high frequencies we approach 90 degrees out of phase, so negative 90, lagging behind the input, right? So it's kind of like, right? It's kind of like I'm pushing the paper, the mass is sliding, and then it's sort of out of phase this way, right? So kind of like that. What this means is we can go ahead and basically put a second data point on our axes over here. So for a very high frequency, we've got another pair of data, and a high frequency is going to correspond to somewhere very far to the right on the frequency spectrum. Okay, so this is omega high frequency, and what we found is that the magnitude starts to approach 0, so it gets very small. So somewhere down here at, say, 0.01 relative to the input magnitude. And we also said, okay, so for this part you kind of have to take my word for it now. We'll determine this analytically later, but right now I'm arguing that the phase at a very high frequency for this type of system is roughly negative 90 degrees. Okay. So I understand this demo is very low tech, but you can kind of imagine, like if we look at this sort of slow motion video that I've produced here, as you start to increase that frequency through the frequency spectrum, you're going to basically be able to plot many different points along these along these axes, right? And so if you were to sort of do an analysis at every frequency along the way, you'd find out that essentially you start to trace out this shape. Okay, so this is a very typical magnitude profile for this kind of first order system, right? And so the theoretical magnitude for infinitely high frequency would just be basically 0. And what ends up happening for the phase is that we start at 0 while the mass is still essentially stuck to the piece of paper due to friction. And as we increase and approach a frequency of infinity, we sort of approach this phase angle of minus 90. Okay, so you can imagine kind of doing this experiment for all frequencies, and this is what you would trace out. Okay, so this demo that we just did here, right? This demonstration basically allowed us to try to visualize the magnitude and the phase as functions of omega, right? Which is the input frequency. And ultimately, as you produce these two sets of plots that are themselves functions of omega, you get this pair of plots, which is called the Bode plot. Okay, so we're going to go into Bode plots, We're going to go into Bode plots in great detail later, but I'm just using this as sort of our very first introduction into the frequency response. Okay, so hopefully you kind of are starting to wrap your head around this idea of what the frequency response represents. Okay, it turns out that if you understand the sort of the shape of the Bode plots and sort of if you understand the frequency response as it pertains to a particular system, you actually have a very powerful set of analytical tools that you can use to analyze the system. Okay, so what we're going to do next is basically answer the question of, okay, so what I said for this demo is based on the little video that I showed you, we were able to get the magnitude and phase for two frequencies, right? So the lowest frequency and the really high frequency, those are pretty apparent what's going on. And then I just said, well, if you could do that experiment for all frequencies, you would trace out these green lines that represent the Bode plot. The question now becomes, well, can I still produce these Bode plots or these green lines, which are magnitude and phase plots for all frequency? Can I do that analytically without having to set up an experiment like this? Okay, of course the answer is yes, and the way that we're going to approach it is through something called the frequency response function. Okay, so the system that we had just set up, so it's basically a mass on top of a movable base. That's got a mass, and there's some damping due to the friction, right? So it's essentially a mass damper system. There's no spring involved, so it's a first order transfer function, and we can model that system by the following: basically just a over s plus a, right? So it's first order because it's a first order polynomial in the denominator, and this is your transfer function that kind of represents that demonstration that we just did. The frequency response function, this is going to become a very important function as we get into analyzing these types of Bode plots and the frequency response of particular systems. And the way to get a frequency response function is basically start with the transfer function and substitute s equals j omega, okay, into that equation. What that does is it gives you a complex valued function, which is itself a function of the input frequency omega. Okay, so for this particular p of s, our frequency response function becomes p of j omega. And then everywhere I see s in the transfer function, I replace it by j omega. So this is a frequency response function. It's a relatively easy thing to compute. But what we want to do is understand that this is a complex valued function. right? What this means is that this function itself can be expressed as a magnitude and a phase, right? This exists in the sort of complex plane. So what we can do, right? What we can do is actually try to express this complex valued function in terms of its real component and its imaginary component. Okay, one way to do that, is to conjugate. Okay, right? I have a complex valued denominator. If I could manipulate this into having a real valued denominator, then I could just separate the real and real and imaginary numerators, and thereby separate the entire equation. Okay, so one way to do this relatively easily is to actually conjugate. Okay, so I'm going to actually rewrite this slightly different. I'm going to write it as a plus omega j, like so. A plus omega j. Now this is a little bit more familiar, right? This is sort of real plus imaginary. The complex conjugate of this denominator is, of course, a minus omega j, right? And if I multiply this out, right, by definition, the denominator is going to be real, right? The denominator should be a squared, right? So basically, anytime you have the product of two complex conjugates, you get the real part squared plus the imaginary part squared, which becomes real because j squared is -1. So my denominator here, if you were to actually expand this out, just becomes omega squared plus a squared, which is all real valued now. What's left to do is to just expand out the numerator. So I've got a squared, and then I have a minus a omega j over the same denominator, right? And what I've done here is I've basically expressed the complex valued frequency response function as a real component plus an imaginary component, right? Being able to do this is very important, right? This is going to come in handy very often throughout this semester. And fundamentally, it comes down to first derive the frequency response function, and then conjugate the denominator so that you can split it up into real plus imaginary components. Okay, the reason we wanted to write it this way, it should become clear if we do a little bit of a complex number review here. Okay, so if we have some arbitrary value in the complex plane, and we'll call this point, say, p of j omega, we know that if we can express this as real plus imaginary, then the magnitude of this complex function, which is essentially the distance from the origin, right? So this is the magnitude of p of j omega. Well, mathematically, that's just the Pythagorean theorem. So that's just going to be the real, it'll be the square root of the real part squared plus the imaginary part squared, like so. And then the phase angle, which is expressed here, right? So the phase angle, the angle of p of j omega, we just have to use some basic trigonometry to figure that out, right? So that's just going to be the arctangent of the imaginary part over the real part, right? Right. So these are basically the expressions for magnitude and phase of a complex number in terms of the real and imaginary components. Okay. So if we apply this concept to our frequency response function, hopefully see where I'm going with this, we can actually get expressions for the magnitude and the phase as functions of omega, which again are basically all the Bode plots tell us, right? So remember that these Bode plots are just expressions of the magnitude and phase as a function of omega. Okay, so let's finish up this analytical work here for this particular problem. So we have our frequency response function written as real plus imaginary. And now we're just going to apply our equations from our complex number theory to derive the magnitude and phase functions. In order to do that, we just have to kind of do a little bit of brute forcing here. Our magnitude of p of j omega, right? We know that's going to be the square root of the real part squared plus the imaginary part. So the square of our real part becomes a to the fourth over omega squared plus a squared, the whole thing squared. And then the imaginary part squared becomes a squared omega squared over omega squared plus a squared squared. And the square root of this whole thing is, by definition, the magnitude of p of j omega. Okay, so if we simplify this, all of this boils down to the square root of a squared over omega squared plus a squared. Right? So this is our actual magnitude function for p of j omega. For the phase, we need to plug into the function arctangent of imaginary part over the real part. So we have minus a omega over omega squared plus a squared. That's the imaginary component. Obviously, we're going to leave out the j because this is simply only the imaginary part. And then we're going to divide that by the real component, which is a squared over the same denominator. Okay, so what you can see here is pretty much we're going to cancel these denominators, and it's just going to be equal to the arctangent of minus omega over a. So pretty quickly you can see that we've developed expressions, right? Analytical expressions for the magnitude and the phase of our original p of s transfer function. Okay, what this means is that we should be able to use those equations to actually, well, first of all, we can verify that what we had experimentally was accurate, but then we could actually trace out, we could compute magnitudes and phases for several frequencies along these axes and actually produce the entire frequency response, or the Bode plots. Okay, so let's just do a little bit of that, test out a couple of numbers here. For our small values of omega, the one that we determined experimentally, essentially, if omega is very close to 0, right, so that's a small frequency, the magnitude is, okay, we're pretty much going to plug in a value of 0 for omega. So the equation becomes a squared over what's practically 0 plus a squared, right, which is basically 1. Right? So we end up with a magnitude of 1 for very small frequencies. Now what you can see is that this magnitude agrees with what we got experimentally, because for that very low frequency where the sort of object was still stuck to the piece of paper, we determined that we had a magnitude of 1. Okay? We can do the same thing for the phase, and hopefully we'll come up with phase of 0. And you can see pretty quickly that if we plug into the expression arctangent over essentially 0 over a, the arctangent of 0 is in fact 0. Right, so we've got our first experimental data point now verified analytically through the use of our magnitude and phase functions. We can check the large frequencies as well. Okay, so experimentally we did a very high frequency one, and this is omega sort of is approaching infinity. So high frequency, the magnitude again is still just the same equation, only this time the frequency is approaching infinity. So it's a very huge number here plus a squared. Now, a is just some finite constant value. If you've got an infinity squared in the denominator, this whole thing tends to zero. Right? So the magnitude itself starts shrinking and approaches zero as the input frequency gets larger and larger. Well, again, that's what we determined experimentally. Right? That was this point on the Bode plot. Way up here at a very high frequency, we found that our experimental frequency dips, and it's almost as though the penny or the mass is just sort of stationary while the paper is just sliding underneath it. The phase, okay, so for the demonstration, I basically told you that the phase is negative 90, and I kind of just asked you to take that on faith, but you don't have to anymore because we actually have the analytical function for the phase. So you can now actually plug in to your equation. So you just have the arctangent of minus, now this is for a very high frequency, so minus infinity over a, and of course that's going to tend towards minus 90 degrees, right? Which validates our experimental findings. The point of doing this analytical approach is now we aren't just limited to testing easy to identify experimental values like low frequencies and really high frequencies, right? We could even test, for example, let's say omega equals 10 times the value a. For that, we can just easily compute the magnitude again just by plugging into our equation. Right? So we get a squared over 10a, which is our frequency, squared, plus a squared. Basically, this boils down to about square root of 1 over 100, or 101 in this case, which is about 1/10, or 0.1. Okay, so what this means is we have another data point, at least for the magnitude, that we can plot. Okay, so at a value of 10 times a, whatever a happens to be, okay, so if a is right about here, right, so a is what's referred to as a cutoff frequency, 10 times that, we can verify that analytically we should have a magnitude of about 0.1. Okay? So we can actually get more data points along that frequency response function, and we could do this for any number of frequencies, right? So if omega equals 100a, just plug into the same formula and you get that the magnitude is about 0.01. Okay, so we have another data point just by plugging into our equations. And what ends up happening is ultimately, right, at the end of the day, we can actually produce a very complete and accurate set of Bode plots. So the magnitude, the phase, and so forth, like so. Like this, you'll actually be able to just sort of point by point sort of construct, just by plugging in several points into your equations, you can actually sort of construct the entire Bode plot point by point. And eventually you do enough points, you just sort of play a game of connect the dots, and you can sketch out your full, accurate, precise Bode plots. All right, so the phase will look something like this. Like so. Like so. Okay. It turns out there's one special point on here. Remember that this was for the transfer function P of S equals A over S plus A. Turns out for this nature, this first order system, there's a special frequency right at A. It's referred to the cutoff frequency. right? The cutoff frequency. So whatever this value of A happens to be, right? If it's 10 over S plus 10 or 100 over S plus 100, the point at which the magnitude starts to drop off uh, and decrease occurs at that frequency, right? So whatever A happens to be, that's where this shape will start to roll off, right? Another fact about first order systems, right? This is a first order system. It turns out that before, right, for all frequencies less than the cutoff frequency, your uh, your magnitude is essentially just 1, right? And then it starts to roll off, and as it's rolling off, for all first order systems, uh, you basically get this phenomenon where it's minus 1 decade per decade in the magnitude plot. And what that means is the magnitude plot, right, it's on a log scale, right? Both of the axes are on a log scale, and this helps us to visualize the frequency response a bit better. So if this is A, this would be 10A, over here is 100A. Well, the slope should be that you're going down 1 decade, right? 1 decade in magnitude for every decade of frequency that you go over, right? So the slope here becomes linear as frequency approaches infinity, and the slope is minus 1 decade per decade. That's true for all first order systems. Turns out for second order systems, it's a slope of minus 2, and we'll get into those details later on as we get more deep into this idea of frequency response. Okay. For now, I'm gonna stop the video here, and this will be the first lecture, the first introduction into the frequency response concept. As we move forward through several more lectures, we're going to get sort of to learn what the application of this idea is and the benefits that we can get by analyzing systems in the frequency domain rather than in the time domain.